picking up where we left off. This is a graph that shows the vapor pressure of several liquids as a function of temperature. So we talked about how the vapor pressure is the partial pressure of that liquid in the gas form above the liquid in a closed container. And we get a dynamic equilibrium that is established. The rate of evaporation depends on surface area and temperature. The rate of condensation depends only on the surface area. And so as the temperature increases, the vapor pressure will also increase. What happens, let's look at water here, as the temperature increases, the vapor pressure increases. And when we get to the vapor pressure being equal to the outside pressure, now even molecules in the interior of the liquid have enough energy to escape into the gas state. And they do so and they form bubbles in the water, which of course then rise to the surface, and that's what we call boiling. Right? So boiling occurs when the vapor pressure of that liquid is equal to whatever the external pressure is. We can see that sometimes a small change in temperature will result in a large change in vapor pressure. So like here, just going up, say 10 degrees, the vapor pressure goes up like 200 torr. So as I mentioned, the boiling point is the temperature at which the liquid's vapor pressure is equal to the external pressure. And now we have not only the molecules at the surface that can escape, but ones that are actually in the interior of the liquid. So the boiling point will depend on the external pressure. So what we call the normal boiling point is the temperature where the vapor pressure of that liquid is equal to 1 atmosphere, which is like normal pressure, right? For water, that temperature is 100 degrees Celsius. So let's think about what happens to a liquid as we heat it up. So here we have the temperature in degrees Celsius, and we're adding heat as we go along. So here we're taking water at 20 degrees Celsius, we're adding heat, and the temperature goes up. And this seems reasonable, right? When we get to the boiling point, to 100 degrees, and we keep adding heat, the temperature does not rise. It stays the same. This seems wrong, right? I'm putting more heat. It should get hotter. No, it's going to stay at the boiling point, the 100 degrees Celsius, until all the water has transformed into a gas. So here, after all the water has transformed into a gas, then the temperature can increase again. The added heat coming in here is replacing the heat that's lost as the evaporation or the boiling happens, because it's those high energy particles that are leaving. And it will also cause the boiling to happen faster, but the temperature will be the same. This figure says, or this question says, use figure 1228 to estimate the boiling point of water at an external pressure of 200 torr. So what we want to do here is we want to find 200 torr and find out where does that intersect the curve for water. So at 200 torr, what is the temperature of the water? Well, we'll drop a line down here. And, this is estimating, and these numbers are not super close together, so my lines are a little crooked, but it's okay. So what do you think the answer is? A, 66. The way I've drawn it, it looks maybe a little more like 70, but it's definitely not 84 or 100 or 0, so 66 is the closest. If you reduce the pressure the external pressure on something, water will boil at a lower temperature. If you increase the pressure, it will boil at a higher temperature. Can't remember if this is, okay, we'll just park here for a minute. So I don't know if you've ever noticed on like a baking mix, like a cake mix, there's a little place that says high altitude directions for the recipe. The reason for that is at high altitudes, like Denver, Colorado is a mile above sea level, 5,000. And you can get higher than that as well. The higher the elevation, the lower the atmospheric pressure and the lower the temperature at which water boils. So if you're cooking something and it's cooking at a lower temperature, then you may need to cook it longer, right? So the baking instructions or the cooking instructions will need to change. The opposite is also true. If you increase the pressure, you can increase the temperature at which water boils. So there's a really old-fashioned thing called a pressure cooker, and the modern equivalent is called an Instant Pot. Heard of those? Right? So it kind of looks like a crock pot, but it's got this lid that clamps on. It's got a little vent, and you can close the vent. You can heat something in there, and as you heat the water and it begins to evaporate, pressure will build up because it's sealed. As the pressure builds up, the pressure gets higher and higher, the boiling point of the water goes up. And so this allows you to cook food faster than you could in an open pot. If you're boiling spaghetti in an open pot of water, it's going to get to 100 degrees Celsius and it's going to stay there. And you can't get it any hotter. In an Instant Pot, you can get boiling water to be higher than 100 degrees Celsius. So there you go, another application of chemistry to real life. As we see in those graphs, the relationship of vapor pressure and temperature is not linear. It's actually an exponential relationship. The vapor pressure is equal to this mess. We can rearrange, do some algebra magic on this to get this form of the equation. This is called the Clausius-Clapeyron equation, after the guys who came up with it. This is not an equation you need to memorize, but you should know how to use it. So the idea here, which is very common in much of science, is doing things so that we have an equation for a straight line. So in this instance, the natural log of the vapor pressure is equal to the y. So on the y-axis, we're graphing natural log of the vapor pressure. Over here, this weird guy, natural log of beta, that's the y-intercept. This is x. So for x, we're graphing 1 over the temperature, and of course that needs to be in Kelvin. And then this is the slope of the line. So you can measure the vapor pressure at a few different temperatures and do some simple calculations, take the natural log and the inverse of the pressure and the temperature, make a graph, we've done that in lab, use a linear regression function, and get an equation for the line. And so then we know what the slope is. The slope is equal to the opposite in sign, -1, times the heat of vaporization divided by the gas constant. And so you can actually get the heat of vaporization from the graph. So this is what a graph like that might look like. So here we have natural log of the pressure versus 1 over the temperature in Kelvin. And if we were doing this, the computer would tell us that y is equal to -3478x. No, they don't give us the intercept. We'll call it 6.75. So this is our slope. Dang it, did that yesterday a lot too. Picked the wrong thing. That's the slope. So the slope is negative 3478. That is equal to negative delta H over R. And there's this weird thing that happens in students' brains that they solve this incorrectly. What a lot of students want to do is they want to say, well, delta H is equal to this divided by R. No. This is equal to delta H divided by R. To get delta H by itself, we need to multiply both sides by R. We can cancel out the negatives there. And so delta H is going to equal R times 3478. Now, there are two values that we have used for R, and the units tell us which one we should use here. This is the one that we use in gas law problems. This has liters and atmospheres in the units. This one has joules in the units. There is a relationship between joules and liter atmospheres. Liter atmosphere is an energy unit, but that it's not a unit that we use when we're talking about energy. So this is the constant that we're going to use. And you do the math and you come up with, I don't know why they wrote it that way, 28.92 times 10 to the third joules per mole. That's 28.92 kilojoules per mole. Now that's obviously not a question that you'll get on an exam, because you would need to graph something on an exam, but there might be a homework problem that wants you to do that. Any questions? So here is an example in the textbook. It says the vapor pressure of carbon tetrachloride is measured as a function of the temperature, and the results are tabulated. Determine the heat of vaporization of carbon tetrachloride. So the way we do this is we make a graph like that. So we would calculate 1 over the temperature for each of these values, 1 divided by 255. And over here, we want the natural log of the pressure. So I'll just do that first one. So 1 divided by 255, 0.00392. And the natural log of 11.3 is 2.425. So you would calculate those values, put them into a graph in Excel, find the equation for the line. I thought I had it graphed out there, but I guess I didn't. So what's more useful, especially on an exam, is this called the two-point form of the Clausius-Clapeyron equation. So if we just know information about 2 of the points, we can calculate delta H. Or if we know delta H and information, we can calculate one of the variables for one of the points. So here we have pressure 2 and pressure 1, temperature 2 and temperature 1, and then delta H. So those are all the variables. If we know, let's see, 4 of them, we can calculate the 5th. And so that's what this problem is going to do. The answer's right up there, that's okay. So this says propane has a normal boiling point of negative 42 Celsius and heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure at 25 degrees Celsius? So we got a bunch of numbers in here. This is not a dimensional analysis problem. This is one where we have to use the equation. And that equation would be given on an exam. I don't expect you to memorize that. But we've got a boiling point of 42 degrees Celsius, and so that's a temperature. We have the heat of vaporization is 19.04 kilojoules per mole. And we have another temperature that is 25 degrees Celsius. So, kind of natural, we'll call the first temperature 1, and we'll call the second one temperature 2. Doesn't matter. There's nothing about pressure in here, except they're asking us for vapor pressure. So this is a little tricky. The normal boiling point is the boiling point at normal pressure. So for this boiling point, what is the pressure? 1 atmosphere. It doesn't come out and say that. So that's something you need to be aware of. So pressure 1 is 1 atmosphere, because that's the definition of normal boiling point. Okay, so now we have 4 variables. So we can use that equation. The natural log of P2 over P1 is equal to negative delta H over R times 1 over T2 minus 1 over T1. And this is kind of a mess, isn't it? Normally, I would say rearrange the equation first and then plug the numbers in. This is not one where you should do that because it gets ugly real fast. If you have a TI-36X Pro, I would recommend using the number solver on this one. So I'm going to rewrite this equation with the numbers plugged into it. So the natural log, P2 is what we're trying to find. So P2 divided by 1 atmosphere, that's going to equal negative delta H, 19.04 kilojoules per mole, divided by R, which is 8.314 joules per mole Kelvin, times 1 over, we need these temperatures to be in Kelvin. So 273 plus negative 42, this is 231 Kelvin. And 25 is going to be, well, actually, since there's a decimal point there, we should use the 0.15. This will be 298.15. Not Celsius, it's Kelvin. That's the whole point of it. So we've got 1 over 231. No, we want 1 over T2. 1 over 298.15 minus 1 over 231.15. And both of those are Kelvin. Just kind of squeezed it in there. So this is the one that we don't know. So you can plug this whole mess into the calculator's number solver and just put an X here for P2, and it'll find the number for you. One thing that we have to be careful with, and this is why we should always include our units, this is units of kilojoules, and this is units of joules. And those units need to agree with each other so they'll cancel out. So I think an easy way to convert this is to say, well, I'm not going to write the kilo, I'm going to write what it means, which is times 10 to the 3. So this is one where you might need to do some writing down of some intermediate values. Over here on the left, it's very convenient that the denominator is 1, because this is equal to the natural log of P2. And then the rest of this big old mess, 19.04 times 10 to the third, divided by 8.314 is going to be negative 2290.1, and that's going to have units of 1 over, no, not 1 over Kelvin, of Kelvin. Times, and this part here, we're not going to try to find common denominators or anything. We're just going to use your calculator. So 1 divided by 298.15 minus 1 divided by 231.15 is negative 0.0009722. And so we multiply those numbers together, and we get that the natural log of P2 is equal to 2.226. Well, let's stick one more digit on it, 2264. We have to undo the logarithm here. And logarithm is a function, so you can't just divide by it because it's not a variable. It's a function, like multiplication is a function, and there is an opposite to it. Division is the opposite of multiplication. The anti-log is the opposite of log, okay? So on your calculator, you're going to have an e to the x button. That's anti-natural log. It's usually near or sometimes even on the same button as the ln. So then P2 is equal to e to the 2.2264. And what the heck did I do wrong? Because I am not getting the answer up there. I'm getting 9.266 atmospheres. Oh. Okay. Phew, scared me there for a minute. The pressure here is going to have the same unit that your other pressure did. They're giving me the answer in torr. Just how sweet of them. Gave me a heart attack. So we need to convert this. And 1 atmosphere is equal to 760 torr. So we multiply by 760. 7042 torr, 7.04 times 10 to the 3 torr. Ooh, got it. This line, I don't know what happened there. Any questions? I know some of you have a hard time with rearranging equations and doing stuff like this. And so if you have one of these 36X Pro calculators, please come and talk to me, and I'll show you your new best friend, the number solver. It'll do all of that for you. If you don't have one of those calculators, this is the sort of problem that, I mean, there will be one on the exam, but this is not a big deal. Using the Clausius-Clapeyron equation is not a big deal, like stoichiometry or dimensional analysis is a big deal. Any questions? Well, what happens if we take a liquid in a sealed container and we heat it. So here we have a little window into such a container, and here, as expected, we have a liquid and a gas. As the temperature rises, the pressure rises as well. As the pressure of this gas becomes greater, it becomes more dense. As we heat the liquid, it becomes less dense. And at a particular point called the critical temperature, these two states are going to fuse into one state that is neither liquid nor gas. It's called a supercritical fluid because it's above the critical point. That's just, one of those weird realities. So TC, the critical temperature, is the temperature at which you get a supercritical fluid forming. Above that temperature, you cannot have a liquid. The pressure there is called the supercritical pressure. Supercritical fluids are really useful as solvents. One use that might be important to you is that supercritical CO2 is used to decaffeinate coffee. So you can get the caffeine to dissolve in this supercritical fluid, and you can wash it away from the coffee beans without taking away the things that give it the flavor that you like, right? And so you could separate off the supercritical CO2 and get rid of it, and it leaves no harmful residues on the coffee itself because it's carbon dioxide. And anything left behind is just going to turn into a gas and float away, and you've just magically removed the caffeine.